Welcome. So welcome everybody. We have today with Stephan. He's a postdoc at Melbourne University and Ohio State, and did his PhD in Munich Technical University. He'll talk today about atmospheric neutrinos, and yeah, it's over.
All right. Thank you very much for the nice introduction. All right. So hello, everyone. I'm going to be talking about observing tau neutrinos, specifically tau neutrino appearance with the JUNO experiment. And this is based on a paper we put on the archive last year together with John Beacom, Nico Bell, and Matthew Dolman, where John is at Ohio State and the rest is here in Melbourne. Now, in this talk, I'm just going to do a short introduction, talking about a little bit about the history of neutrino oscillations, because I think part of it is pretty interesting. I'm going to give a very, very short crash course on oscillations, just to remind everyone what we're kind of talking about. A very short introduction to atmospheric showers, because that's going to be the source of neutrinos we're going to be using for this analysis and these predictions. And then I'm going to give a introduction to how neutrino oscillations using atmospheric neutrinos were actually discovered, so that we then have a baseline to how the proposed analysis we made for JUNO differs from that. And then we're going to talk about searching for tau neutrinos. We're going to talk about the challenges, why it hasn't been seen yet in atmospheric searches. We're going to discuss a little bit some unique aspects of liquid scintillators, because unlike hyper K or super K, which are water-based, JUNO and CamNAND, which we'll get to, is liquid scintillator-based, so essentially carbon. We're going to look at a inverse beta decay search, and why that's interesting for this search, and we'll get to. And then we'll do a prediction for JUNO with the results, and also how these can be improved, and some aspects of BSM physics we can use these types of analysis for. And as a quick reminder, we're talking about the little tau neutrino here. And this is the paper this is based on. All right, so let's get to it. Now, some history to all of this. So in 1956, originally, Ponte-Corvo here published a paper discussing oscillations, but just as a side paragraph based on kaon oscillations. And then in 1958, he brought out another paper where he actually started discussing neutrino oscillations. And the basic idea is very similar to what kaon oscillations, which were the hype topic at the time, because they were just recently, the parity violation was essentially just recently seen or predicted. But essentially, his idea was there is a new neutrino state, which is even weaker interacting than the weakly interacting neutrino. And then there's an oscillation between the neutrino and its anti-state. And that's why the neutrino then would be composed of either a symmetric or anti-symmetric combination of fundamental states. And interesting for today is actually he called these new very weakly interacting neutrinos steriles, which is something we've kind of kept until this day. But still, at this point, people thought neutrinos could only come in one flavor, so that electron neutrinos, muon neutrinos, and tau neutrinos exist was not really a thing yet. But then 1962 happened, so the Brookhaven experiment, which actually showed that muon neutrinos oscillate to muon neutrinos and electron neutrinos are separate things. So of course, like any good physicist, Ponte-Corvo dusted off his old analyses and rewrote it in a way that now electron neutrinos and muon neutrinos are oscillating essentially to their anti-states, or yeah, to their anti-states. And then I have some quotes here from him. So for these first things, he said then, okay, so they're oscillating to these anti-states, and these anti-states for him were not visible. Because they have incorrect helicity, so they're unobservable, and he called them sterile again. So steriles were still a big deal for him. But then also, and this is for me kind of interesting, he predicted the solar neutrino problem. Because essentially what he said is, right, if you have an electron neutrino being produced in the sun and then flying towards the Earth, it will oscillate to its sterile state and not be observable. So then the flux of solar neutrinos will be less. And this is kind of what we see, but of course the reasonings are a bit different. But that's just this interesting little side note. But he is the first person to actually discuss neutrino oscillations. Now, how we actually think about it these days is a bit more involved, not too much, but here's a quick crash course. Right, so we look at neutrinos and we separate neutrinos into their flavor states, which are essentially their interactions eigenstates, and their mass eigenstates, which are essentially their propagation eigenstates. And that's important, an important distinction, because now neutrinos interact based on one state, and they propagate based on another eigenstate. So what can happen is you start off with a neutrino, and it starts propagating, and its constituent mass eigenstates start oscillating. And now, if the mass eigenstates have a different mass, they will be oscillating at a different frequency. So this is essentially a plane wave where the oscillation frequency is defined via the mass of this mass state. And then here's a little snippet of how you can imagine this, right? You have your flavor eigenstate, so the thing we actually usually call a neutrino. And then, as any good things, it comes in three flavors. And so essentially you have these three flavors with different masses oscillating differently, so with a different frequency. And then along its path, you can like set different little slices, and the composition of the original neutrino and of its three mass eigenstates will have changed, even though you've not touched it. And this is essentially the origin, or how we imagine neutrino oscillations happen these days. Now, actual calculations are a bit more involved, but it's just a lot of linear algebra. And then there's some other effects, which I'm not going to be discussing here today, something like the MSW effect. So essentially how neutrinos oscillate when propagating through matter changes a little bit. CP violation, so essentially differences between nu and nu bar oscillations. Parametric resonance, which you can not really disentangle from mass oscillations, etc. So there's a bit more to it, but as a very basic thing, all we need to know for this talk is, depending on the distance traveled, neutrinos will oscillate. All right, and then the next point, where do we actually get neutrinos from? Now, historically, so when the original oscillations were proposed, we were actually not thinking about atmospherics. What people were thinking about back then were solar neutrinos and reactor neutrinos. But there's a problem with solar neutrinos. There, we can't really disentangle other effects from it, for example, the solar model or whatever. And we don't have a good baseline for how many neutrinos are actually being produced at the start. So that's a challenging way to look at neutrino oscillations. Now, reactor neutrinos, and so essentially long baseline experiments, seem to be an ideal case, because there we know the number of neutrinos being produced, and then we have a good baseline of how many are produced and then how many do we actually see in our detector. The problem with that, though, is at the time, people were imagining the mass splittings to be of the order like an EV. So huge compared to the actual numbers we think they are today, which is 1e minus 3 and 1e minus 4/5, depending on which mass splitting you're looking at. So that changes the oscillation length in a major fashion. And the reactor experiments at the time were sensitive to a combination of parameters where essentially the mass splitting was of the order of an EV. So that didn't work because that's not how late nature is realizing this. So this is where atmospheric neutrinos came in. Atmospheric neutrinos are constantly being produced in the atmosphere via cosmic ray interactions. So we have this stream of cosmic rays constantly bombarding our atmosphere and producing pions, kind of sketched out here on the left. Now, essentially, pions also come in 3 flavors: pi plus, pi minus, and pi naught. What we kind of care about here, though, is pi plus and pi minus, and let's ignore the pi naughts. Now, when you produce a pi plus and pi minus, these things can either interact again, which they often do, or they decay. And when they decay, they produce a neutrino, which is significant for us, but they also produce a muon. And this muon, in turn, can decay again and produce 2 more neutrinos. It's kind of shown here. So the steps are essentially, we have protons colliding with air nuclei. We produce a whole bunch of pions. These things decay. While they decay, they produce a muon neutrino or anti-muon neutrino and a muon. And then this muon also decays, producing more neutrinos. And looking at this chain, we can already see the number of the ratio of flavors we expect, which is going to be 1 to 2 to 0, which is essentially we expect 1 electron neutrino for every 2 muon neutrinos, and we expect 0 tau-neutrinos. Now, we'll get to how we fix that later, but just keep that kind of in mind. And now, looking at this very simplified picture, this is actually how a cosmic ray looks. So they're actually gigantic. This is an 8 by 8 square kilometer slice of Chicago, and this is a 1 TeV, so actually a pretty low energetic cosmic ray, showering 20 kilometers above Chicago and essentially just covering this slice. So you can imagine that actually modeling these things is a bit more complicated than what I'm talking about, but everything here on the left is good enough to understand what we're going to get to. All right, so let's talk about our expectations when trying to measure atmospheric neutrinos. Now, if you have your little detector up here and you're looking into the sky, into the Earth, essentially these showers are coming from all directions on the Earth, right? And we can parameterize the incoming directions by this theta parameter, where if the cosine of this thing is 1, it means it's coming straight from above at you. And if it's -1, it means it's coming through the Earth at you. Now, this is important because this is essentially our placeholder for the distance the neutrino travels. The reason why distance is important is because the oscillation length is a very important factor of this discussion. Now, to symbolize this, let's talk a little bit how this looks. When you have a muon neutrino propagating either from the top of the atmosphere up here to you or through the Earth, the baseline is very different. So neutrinos are usually produced, or particle showers are usually happening about order 10 kilometers above us in the atmosphere. So they're only traveling order 10 kilometers to the detector on the surface, or maybe 1 or 2 kilometers below the surface. So not really that far. But then when they travel through the Earth, they travel 12,000 kilometers at its maximum, which is a very long baseline. And these numbers are kind of significant because the oscillation length, so the period of how far they have to travel to oscillate, is roughly 1,000 kilometers for every GeV in neutrino energy. Meaning, in turn, at low energies, so like 100 MeV, so 0.1 GeV, it's only 100 kilometers. And this is kind of how we can explain this figure on the right. So these yellow bands are essentially zero survival probability, meaning the muon neutrino, sorry for the lack of index, has oscillated to something else. We don't know what yet, but something else. Or the black band means it's stayed alive, so it has stayed unchanged. And in this figure, what you kind of see is, okay, so if it's coming from above us, which is up here, for down to pretty low energies, the neutrino actually doesn't care about oscillations. So it's not really doing anything in this big black blob up here. Now, below the horizon, the distance is changed by a lot, and suddenly the oscillations become relevant. And then at low energies, because the oscillations length also scales with energy, oscillations actually start happening even when they're coming from above us. Now, the keen-eyed observer amongst you might also see that this kind of looks weird. It looks like you have here one type of oscillation and over here another type. And that's what we historically call, for this type over here, like atmospheric oscillations. And over here, we call them solar oscillations because the parameters driving these oscillations were measured using those types of experiments. Okay, so this is our expectation. This figure here, meaning essentially we think when stuff is coming down at a GeV, it's probably not going to be oscillated. If it's coming up, it should be oscillated. All right, so keep that in mind. So how do we now use that? Well, we try to detect them. And the way we detect neutrinos is we build a big tank filled with a clear medium, like water. Now, why do we need a big tank? Well, the neutrino cross-section at these energies is something like 1e minus 38. So it's minuscule compared to a proton cross-section, which is roughly 14 plus orders of magnitude higher than the neutrino cross-section. So we need a big, big volume for these things to actually interact. So we go big. So Super K was built. Super K itself is a 50 kiloton water tank filled with light detectors on its surrounding surface. And just to illustrate how absolutely insanely huge this thing is, this is a boat filled with 2 people. So this thing is absolutely gigantic, and it's filled with ultra pure water. And now the way neutrinos are detected is pretty simple. Well, kind of. So what happens is a neutrino flies into your detector. It interacts within the detector with the hydrogen atoms in your water. And it undergoes something called a charge current interaction, which essentially means the neutrino is going to produce its associated lepton via a W boson exchange. This associated lepton, so for muon neutrinos, the muon, and for electron neutrinos, the electron, will then fly through your water at relativistic speeds, specifically at a speed higher than the light speed within water. And this produces something called Cherenkov light. And this Cherenkov light is emitted in very specific cones with a very specific angle, depending on the refractive index of your medium. And then you get these beautiful rings, which Super K essentially sees on these photo multiplier tubes on the surface here. And they can use these things to distinguish particles. So this is what Super K sees. And to sum it up, how to detect neutrinos is in this case, you look for a neutrino interacting with your detector, producing the associated lepton, and then detecting the light from that lepton. Now, that's a fairly straightforward process for particle physics or in particle detection. So let's apply this. And it worked very well. So this was our expectation over here. And as a reminder, we expected downgoing events to not be oscillated and upgoing events to be oscillated. And this is what Super K measured. This is a bit more modern data than they actually used for the discovery, but it shows the shtick very well. So for example, here on the bottom plot, we're talking about energies above, deposited energies above 1.33 GeV. And what you see is on the, so upgoing, there's way less muon neutrinos that with oscillations than without, and that's what the detector actually saw. But then downgoing over here, there's more muon neutrinos than upgoing. And this aligns with both the with and without oscillation line. And then at low energies, there is a similar asymmetry across the sky, but it's even the asymmetry is not as strong, and the flux of muon neutrinos is lower than the flux of muon neutrinos without oscillations, even for straight downgoing, which is also what we expect according to this figure, because at low energies, muon neutrinos are also oscillating. And this observation was what got these two gentlemen the Nobel Prize. While I've been focusing on Super K a lot, also McDonald from Snow Lab shared the Nobel Prize for the discovery of neutrino oscillations in 2015. And this is based on data from 1997, roughly. So this established neutrino oscillations, which is a huge deal because in the standard model as well, right, we don't expect neutrinos to have mass. So this means we now have something in addition, which is new physics, which has also got the theory community very excited. Okay, but I've now been always talking about muon neutrinos. And Super K did the same thing with electron neutrinos. So they have the same type of measurements using electron neutrinos. But now the interesting point is, what about tau neutrinos? Right? So we have used two flavors, but we know we think there's a third flavor. So why haven't we seen that? What is its effect? So let's talk about the third flavor a little bit. So until now, in Super K, as mentioned, we've been talking about these two things, or specifically more usually the muon neutrino. But here, now we're talking about the tau neutrino. So again, we're going to look at how we measure it via charge current interactions, typically. So we have, this is a typical charge current interaction. You have a neutrino coming in, exchanging a W boson, so weak force interaction, that's why it's so small, with a nucleus, destroying the nucleus usually in the process to some weird jet combinations of pions and gluons, and then exiting associated tau, which has a short lifespan and decays to a tau neutrino, and again, a shower. And this is the important part. It decays again, unlike the electron and the muon, which within the detector size don't really decay, where the muon could decay, but the electron cannot. But if the energy of this thing would be high enough, what we should see, and this is an example from a different neutrino experiment called IceCube, we should see the first interaction, so the exchange of the W boson over here, and then the tau kind of propagating a little bit, and then decaying and producing another blob. So what we're looking for now in these charge current interactions is two blobs, very close to each other, typically called double bang events, which is a combination of two cascade events. Okay. Well, let's try to work with that. But there we run into huge issues right away. We don't produce tau neutrinos in the atmosphere. So we need the muon neutrino to oscillate to a tau neutrino. And this is a problem because, as I showed before, right, per GeV of neutrino energy, the oscillation length is 1,000 kilometers. So we want the neutrinos to be low energetic so that they maximally oscillate to tau neutrinos, so that they oscillate very rapidly to these tau neutrinos. But we also want the tau to decay in a visible distance. And this actually wants us to go for high energies. Because the tau is so massive compared to the muon, for example, it decays very, very quickly. So what this means is essentially if it decays about after 5 centimeters per TeV of energy. So that means into these detectors, you need a super energetic tau to fly through to decay at any sensible distance, so you can disentangle the first interaction, so this W exchange, which is producing a blob or a cascade, and the decay of the tau, which again is producing a blob or a cascade. So we're now kind of caught between a rock and a hard place. On the one hand, we want to go to low energies, so we have as many tau neutrinos as possible. But then on the other hand, we want to go to high energies to actually see the tau, which is produced via the charge current interaction. So a good question is, of course, now, how do we actually solve this? And this is an issue, and this is the reason why atmospheric experiments until now have not seen the tau neutrino, because they couldn't identify it. Well, honestly, one of the solutions is to give up and just go home, or give up on actually measuring the tau neutrino itself, but trying to measure the effects of the oscillations to tau neutrinos. And this is what I'm going to be focusing on here. This is very much along the lines of how beamline experiments work, where they have a beam of a certain flavor of neutrino, where they know how many are produced at the start, and they look for these neutrinos disappearing, so oscillating to a different flavor, and then counting them at a certain distance. And so they measure at this distance less than the produced neutrinos. And so that's called disappearance. So essentially, our idea is to take the muon neutrinos produced in the atmosphere, as discussed before, not specifically look for tau neutrinos, but instead look at the effects of these new mu's just disappearing, so going to something else. All right, so how do we do this? How do we use this fact? Because, right, we don't really know well how many atmospheric neutrinos are being produced. Well, kind of. We do know from we know from super K roughly how many atmospheric neutrinos are being produced, because we have these types of measurements here on the left, specifically these ones down here, where we measured the unoscillated neutrino flux. So we can use these types of angle binned measurements to get the oscillated neutrino flux over here and the unoscillated neutrino flux over here. And then with a bit of trickery and using some other experiments like beamline experiments, which measure oscillation parameters, we can do the same thing for lower energies, where while we can't just use the super K experiment in combination with reactor-based experiments, which have very precisely measured some oscillation parameters, we can even use the low energy data to extract the unoscillated neutrino flux. And then instead of looking at the angle bin thing, let's just look at the total. And this is something super K does as well in their analyses. And it looks something like this. You have a dashed line up here, which is the neutrino flux produced in the atmosphere, and which would arrive at the detector assuming no oscillations. And you have the actually measured neutrino flux with the black dots here, and then the theoretical prediction with oscillations. So as you can see, again, the oscillation effect is very strong and very visible. But this part here, so this green band essentially, is muon neutrinos vanishing, going to a different state. Now, I did not show electron neutrinos in this plot here. And the reason for that is because in the grand scheme of oscillations, on this scale here, the line, the electron neutrino line with and without oscillations doesn't change that much. We account for it, of course, but for the discussion here, it's not important. So the important part here is this is what is this blue dashed line is what is being produced in the atmosphere, but this pink line is actually what we're seeing, and the band in between had to go somewhere. All right, so how do we measure all of it? And this is kind of where the measurements now start differing from the typical experiments. As I mentioned before, typically we look at charge current experiments where we can distinguish flavors because a neutrino produces interacts and produces the associated lepton. But in this case now, we want the total. So we don't actually care about the neutrino flavor. So this opens up the possibility of using neutral current interactions, where every neutrino flavor within a good agreement interacts in the same way. And every neutrino flavor will be measured if you do a neutral current measurement. So if you then have a neutral current experiment, for example, JUNO, you can take these measurements by super K and inject them into JUNO, and then you get these lines. So essentially, if you inject the pink line, which again, I remind you, is the muon neutrino flux after oscillations, you get this bottom line here. And then if you inject it without oscillations, you get this top line here. So if muon neutrinos oscillate to tau neutrinos, what we expect to see in these total neutral current measurements is this top line. And then we have the bottom line from super K to compare with. Now, as a side note, and this is kind of what this figure here on the left shows, is at low neutrino energy, so at 100 MeV, we expect roughly a flavor ratio of 1 to 1 to 1, just because the neutrinos have oscillated so much that they're oscillating so quickly that within the detector tolerances, they've oscillated amongst each other and evened out. So very roughly speaking, if you can measure the entire neutrino flux, 30% of those should be tau neutrinos. So let's talk about measuring these things then. Well, so one thing which was weird and what happened here is our x-axis changed, and we never liked that, right? On the left, we were showing neutrino energy, and here on the right, we're suddenly showing something different, namely neutron energy. So what happened there? Well, in liquid scintillators, which is JUNO, they use carbon, essentially soap, instead of water. And the way a neutral current interaction works with a carbon target is you have a neutrino coming in, interacting with your carbon-12, knocking out a neutron, and leaving the carbon atom in an excited state. And this state then decays. And as a picture, this kind of looks like this. You have a neutrino of any flavor coming in, interacting with your carbon, knocking out a neutron and possibly some other stuff. This neutron will have roughly this energy, so E squared, the energy of the neutrino squared divided by the mass of the neutron. It will propagate a bit, roughly 20 centimeters or 40 centimeters, and be captured after roughly 200 microseconds by a carbon atom or a proton. And this then emits a photon with roughly 2.2 MeV, while also a neutrino exiting, but we don't care about that because neutrinos, if they don't interact again, aren't visible. And in all likelihood, this exiting neutrinos will not be interacting again. But so the interesting thing about this signal here is we can tag these things. So this is very interesting for experimentalists because we have this high energy photon being emitted after a very specific time after the original interaction. So this type of interaction is a two coincidence measurement. You first measure the emission of the neutron and the emission of maybe some other particles. And then you measure the capture of the neutron. And then this happens on a very specific time scale, so we can do some nice cuts. And now, as a fun side note, and one of the reasons why this works well in carbon versus water is, first of all, in water, neutrons capture very poorly. And then also at lower energies, we just get way more light in a liquid scintillator than in ultra pure water, roughly 100 times more light per MeV. So this gives JUNO a higher sensitivity to lower energy events versus super K, for example, which super K is kind of fixed now by adding gallium to its detector, but we're going to ignore that for now. All right, so again, what are the main differences between our previous study of neutrino oscillations using super K? First off, we have a more complicated event topology. So we're now, instead of looking for a single lepton flying through the detector, we're looking for an interaction point plus a capture of a neutron. And then another point is the light being emitted here is not from ionization or Cherenkov light, right? Because this neutron here is not charged. So this means what we're looking at is actually scintillation light, not ionization or Cherenkov light. And this makes things also more complicated. So, and what do I mean by more complicated? Well, here on the right is a picture of what you would kind of expect. If in the solid line, this is the neutron being knocked out by the corresponding neutrino energy. So if you inject like a 1 GeV neutrino, you get something like 100 MeV to a 1 GeV kinetic energy neutron as the solid line here, and a similar picture for a 100 MeV neutrino with the solid line here. But a liquid scintillator detector doesn't actually see the kinetic energy, it sees scintillation light. So what it sees is the neutron being knocked out with a high kinetic energy, and then it starts bouncing around within your detector, exciting carbon atoms, or bouncing off of protons and producing recoil light. And you measure that light. And when you measure that light, it looks very different than an electron ionization track. And so what you actually see is a suppression or a quenched light signal, which are these dashed lines. So essentially, you'll be reconstructing a neutron with a lower energy than it actually has. Because our typical reconstruction algorithms are based on ionization for electrons, not for the scintillation of neutrons. So you can, of course, correct that, but this is the energy you will actually see in your detector, which is lower than the kinetic energy of the original neutron. Okay. So, and now there's another thing you can kind of maybe see if you're seen these types of searches before. This interaction here looks similar to something called an inverse beta decay event. Why do I say that? Well, in an inverse beta decay event, an anti-neutrino is captured by a proton and it produces an electron plus a neutron. Now, in this case, if this is the case, so if they look similar, inverse beta decay events have already been used to look for example, the DSNB, so low energy astrophysical neutrinos. Maybe we can use this type of search for this type of analysis. So we go to current experiments, namely CamLab, which has done these types of inverse beta decay searches. So to a quick recap, the reason why they look similar is, okay, so in our neutral current interaction, you have a neutrino coming in, knocking out a neutron from the carbon atom and leaving the carbon atom in an excited state, which isn't that important. And in the inverse beta decay interaction, you have a anti-neutrino being captured by a proton, converting it to a neutron plus a positron. Now, this neutron here is low energy, and this positron is high energy. In our case, though, the neutron is high energy. So what this happens here is essentially this neutron is faking the signal from your positron and your neutron in an inverse beta decay search. So let's look at these searches and see if we can get our neutral current event rate to align with what the actual data sees in these inverse beta decay searches. And for that, we have to do some refinements, right? We first have to look at the detector a little bit, which is CamLab, which exists currently and has been running for a long time. It's a 1 kiloton liquid scintillator detector, so it's a fair bit smaller than Super K, but it is liquid scintillator, so let's work with that. So what we introduce then is some cuts. We introduce a timing cut, which I kind of already showed off, where we expect the neutron to propagate for roughly 200 microseconds. So we can introduce a cut on that. We can introduce a cut on energy, right? Because in these DSNB searches, you expect very low energy events. So that's what you're targeting. And you can introduce spatial cuts because the neutron will propagate a certain distance. You can draw a little bubble around the original interaction point and only consider events which are contained within that spatial distance. And in the end, what happens to your signal or to your neutral current events is shown here on the right. Originally, the neutral current events without cuts looked like this dashed line. All of this is normalized to the same number. But then after cuts, we are enhancing the lower energy events here. And there's like a peak around 250 MeV. So most of our events are actually coming from between 100 and 300 MeV, and then some minor contribution from higher energy neutrinos. But can we reproduce data is the big question. And the answer is yes, we can. So this is what CamLab measured. And what we injected is the neutrino flux without oscillations. And we align fairly well with the actual measurement by CamLab. Now, the problem with all of this, of course, is CamLab is small and has only seen very few events, right? We're here talking about like 20 events or 15 events, depending on how you do your cuts. And we can't really distinguish a 30% change with these type of statistics, which is what we're expecting if muon neutrinos go to tau neutrinos, right? So we need a precision which can see a 30% change. And with an order 10 events, that is roughly the statistical uncertainty you have, right? If you take the square root of 10, you get 3, so that you have a 30% precision. So that's kind of what CamLab is working with. So it's not good enough to perform this type of search we're wanting because it doesn't have the statistical power to do it. All right, but JUNO might. So the reason why we say might is because we just make CamNAND bigger, and we make it way bigger. So we make it 20 times bigger. So this is now 20 kilotons of liquid scintillator, putting it roughly in the same ballpark as Super K. There's also some additional perks to using JUNO. First of all, it has a better photoelectron yield. That's because they tweak their liquid scintillator a bit so that more light is being produced. And they don't, unlike CamNAND, they don't have a balloon in the center, which means essentially you have to introduce some additional cuts. So on a very basic level, we expect JUNO to see 20 times as many events over the same time period as CamNAND, which would give us the statistical power we need to actually see the effect of tau neutrinos, right? Because originally we were at, let's say, roughly 10, now times 20, let's say we're roughly at 100, and suddenly our precision has gone to 10%. And then if we add some factors, it might go down to a few percent level. And that's good enough to see a 30% change. So let's work with that. And this is what we get. So we have CamNAND, where we kind of did a good prediction of the data. And now we're doing a prediction for JUNO, which will start taking data this year. And we look at here 10 years of data. Now, I kind of alluded to this. The 20 times is conservative. It's actually going to be better because some cuts and some light yield efficiencies are better. But in the end, what we expect is a count or a rate spectrum, depending on the energy of the neutron, like this. And what we expect is without oscillations, so or without new tau. So when we're injecting the pink line from the Super K plot, which I showed earlier, we expect this bottom line here. And if we inject the without oscillations, so all neutrinos, we expect this dashed line up here. And in total, that means we're looking at a difference of roughly 140 events between these two, which on a pure statistical level would give you a significance of 7 sigma with 10 years worth of data. So what does this mean? How do we contextualize this? Well, in the grand scheme of things, what we're looking at is low energy neutrinos, and we are claiming that JUNO can see or reach a 5 sigma sensitivity within 5 years of data taking time. And they're probing very different energies than all previous searches have done until now. And they would also beat all current searches, which have not reached yet the 5 sigma discovery limit we've set for ourselves. So these are current measurements by Super K, Deep Core, which is an IceCube subset experiment, and IceCube, which uses astrophysical neutrinos. So we're predicting that JUNO will be able to beat all other atmospheric experiments in the hunt for tau neutrino. Now, some side notes. I did not show reactor experiments here. Reactor experiments have actually undergone major changes and improved a lot. Because we had a more precise handle on the mass square differences, we are more aware of what baselines we need to measure things. So actually, APRA has already seen the tau neutrino appearance at higher energies, so at roughly 7 GeV. So reactor neutrinos have already been successful at seeing tau neutrino appearance. But we are hoping that JUNO can use atmospheric neutrinos to see tau neutrino appearance at a very different energy scale, which would be very exciting. And this is not the end of it. this is actually our conservative estimate, and I'll get to why in just a moment. We don't think 5 sigma in 5 years is good enough. So let's talk about how we can improve this. Well, okay, so I denoted the energy region we're looking at here. And honestly, and for lower energies, it's not really possible because you run into solar and reactor neutrinos. So this zone over here is the no touching zone. Your analysis will die over here. But there's no real reason to constrain it to the energies here. The only reason why we did it is to compare it to current inverse beta decay searches, which target this energy region here. But for this type of neutral current search, there is no reason to restrict yourself here. And that would give you roughly 30% more events if you go to high energies, so a few hundred MeV. Now, there's a few other things which are more detailed, which we assumed in our calculations, which are conservative. First of all, for example, we used a selection efficiency, a conservative selection efficiency based on the CAMLand calculations. But JUNO themselves have already put out a paper that their efficiency will not be 80%, but 95%. Additionally, we've used a live time of 80%, which is equivalent to the CAMLand live time. But actually, JUNO should have something more in the order of 93%. We've also cut all proton final states. So when the neutrino undergoes a neutral current interaction with the carbon, there is no reason why it shouldn't knock out a proton instead of a neutron. We were cutting these, again, because we were comparing to inverse beta decay events. But in such a dedicated search, you could include those, and that would straightforwardly just give you twice as many events, roughly. And then you could improve things with possible directionality, but that requires a lot of work and is more involved and maybe not feasible, so let's ignore that. So ignoring directionality, these points where we were very conservative originally and correct them to what the collaboration themselves say they can reach, gives you 3 times as many events, meaning JUNO can reach a 5 sigma sensitivity within 2 years of data taking, which we find very exciting. And that means they would discover atmospheric new tau appearance within 2 years once they start, which they are hopefully starting this year. And now, as a final point, let's discuss, can we actually use this for BSM studies? And the answer is probably yes. And why? Well, we are actually kind of already doing a BSM study to look for this tau neutrino. Because essentially what we're comparing ourselves to is this pink line, which, as you recall, is the oscillated muon neutrino line, to the total neutrino flux. Now, if sterols exist, some of the neutrinos would be oscillating to a sterile state, meaning in the end, JUNO would see less events than this blue dashed line we show up here. So if you can get the precision high enough, you can start looking for changes into your event rate and use that for sterile searches, because you're essentially looking for neutrinos vanishing to a sterile state, which is cool. And then there's some other things you can do. There's, for example, boosted dark matter, which a colleague of mine has done and made predictions with, which targets similar energy ranges. You can look for unique nuclear signatures, which Ohio State has done, which is also in a similar energy range. And these are just some examples of how we can use this new type of event signature to look for BSM physics. But there more hopefully to come. All right. So with that, I'm coming to the end of my talk. And here are some take-home messages. In this talk, I've introduced a new way to probe new tau appearance using atmospheric muon neutrino disappearance which is very similar to what reactor experiments do at a different energy scale. We compared precision measurements from Super K and JUNO, charge current and neutral current events respectively, to set these, to make these predictions. But of course, JUNO could also itself measure the neutrino flux, and then some degeneracies in the cross section wouldn't exist between Super K and JUNO. And then we are claiming that the next generation of neutrino observatories will be able to reach a 5 sigma sensitivity for this new tau appearance. And it should be able to do it within less time than 5 years. And with that, I've come to the end of my talk. Thank you very much. Are there any questions?
Okay. Thank you. That's a great talk. We're open to questions now. Anyone? There's one online.
Does the I just wanted to know if the like a 5 sigma measurement of the new tau appearance, does that neatly lead to like a improved constraint on like theta 2-3 or mass splitting or anything like this?
Yeah, it specifically, it would not supersede current reactor experiments, but it would be at a different energy scale. So essentially, you would be probing these parameters, the energy dependence of these parameters.
So I had a naive question. So,
Yep.
So presumably, I mean, the uncertainties in something are, well, let's say estimates, right? How good, like, how well do we, like, if you're really claiming that, you know, like 2 years and 5 sigma or something like that,
Yeah.
How realistic are the estimates of?
I was being a bit, yeah, I was hiding a big fact, namely neutrino cross sections at these energies.
Okay. So that's a different question altogether. But
yeah, so no, but that kind of runs into things. So the predictions we've made, right, these 5 sigma levels, this is purely statistical. So you would have to include, but we did include things like detector effects and whatever. What we did not include were systematic effects, and specifically from a systematic point of view, the most important effect is the uncertainty on the cross section.
So are you using Gini? So what are you using?
We're using Gini, yeah. And the problem with the cross section, honestly, is it in itself can have a order 10% uncertainty, right? And we are looking at an order 10% effect for this new tau appearance. So they're roughly the same scale, which is a problem. So they're also degenerate, which is another problem. So what one would have to do is either have an additional lab experiment to have a neutrino carbon cross-section measurement, or JUNO itself would internally have to be able to use some other energy region or some other event topology to calibrate the neutrino cross-section and use that for this type of analysis. Does that kind of answer your question?
Yeah, sure. I mean, I was not even thinking about the cross section itself, because that opens a can of worms. I mean, that's, you know,
that is the major can of worms we have. Most other parameters are or uncertainties are very subleading compared to that.
I see. Okay, yeah, that was my question. I mean, neutrino cross sections are issues. Is an issue. I mean, that's a completely different, you know, like.
Oh yeah. since you mentioned Genie, if you run Genie in different settings, you get very different results,
Yeah.
which is fun. So yeah, that is an issue.
Okay, thanks. Yeah.
Was there another?
More questions? If not, I think we could end now. Thank you very much again.